If you saw the earlier Cisco ACI fabric architecture deep dive, you already have the foundation. We covered the spine leaf model, what APIC handles, and how traffic moves across the fabric. In this video, we build on that and focus specifically on the hardware families and the protocols that make forwarding work. So think of this as the companion to that architecture dive. This time we are zeroing in on the hardware generations and roles of ISIS, COOP and MP-BGP EVPN so you can see exactly how forwarding comes together in ACI. Hardware sets the capability. Protocols decide how forwarding actually works. First, a quick hardware overview. Leaves connect endpoints and apply policy. Spines move traffic across the fabric. Leaf spine provides equal cost paths for scalability and resilience. With the basic fabric roles in place, the next step is understanding what the hardware names actually tell you. You don't need to memorize every model number. Just learn what the suffix families are signaling. EX, FX, ECR2, FX3, GX, GX2 and H series tell you the ASIC generation and capability tier. In general, newer suffixes mean more scale, newer silicon, better telemetry, stronger security, higher speeds or deeper buffers depending on the family. EX is the older cloud scale baseline, the first wave of true cloud scale ASIC leaf nodes supporting early microsegmentation features. FX and FX2 step up from EX with better telemetry, larger tables, and stronger all-around capability. FX3 stands out mainly because it adds line rate MACsec. H series is a newer refresh that can add platform enhancements, deeper buffers, or timing improvements depending on the model. GX and GX 2.2, newer silicon, bigger 100G and 400G scale, and more room for long-term growth. H series is a newer refresh that can add platform enhancements, deeper buffers, or timing improvements depending on the model. To audit any ACI fabric, you need to decode Cisco's naming schema. Every part of a Nexus model number reveals its physical capabilities. The N9K prefix designates the Nexus 9000 platform, while the letter C identifies a standalone switch chassis. The series digit dictate its architectural role. A 9300 indicates a fixed leaf switch, while a 9500 designates a modular spine chassis. Finally, the remaining characters identify port density, interface speeds like YC or TC, and the specific cloud scale ASIC generation. That's enough on hardware. Before we get into ISIS, COOP and MP-BGP EVPN, it helps to place LLDP, DHCP and NTP in the picture as bring up and operational services. Then we can move into the main forwarding and control roles. At a high level, LLDP, DHCP and NTP handle discovery, bootstrap and operational timing. ISIS provides built-in underlay reachability, COOP tracks local endpoint ownership and location, and MP-BGP EVPN is used when reachability extends beyond the local fabric. Start with ISIS because in ACI it's the built-in underlay foundation the fabric uses underneath everything else. Inside an HI fabric, ISIS is the internal protocol the fabric uses to maintain node-to-node underlay reachability. That includes the loopbacks, taps, and other node identities the fabric uses internally to move encapsulated traffic where it needs to go. ISIS is a link state protocol, which means each node learns the topology and calculates best paths from a shared view of the fabric. That matters in a spine leaf design because the topology is highly regular. Every leaf has parallel upstream choices through the spine layer. When multiple equal cost paths exist, ISIS can install them naturally. That gives ACI the ECMP behavior engineers expect in a leaf spine fabric. So, if a packet needs to get from one leaf to another, the underlay already knows several valid transit options through the available spines. Another big benefit is fast convergence. If a link or node changes state, link state protocols can propagate that update quickly and recalculate paths without waiting on slow hop by hop discovery. That is one reason ISIS is such a natural fit here. The fabric is structured, the path options are predictable, and the protocol handles topology intelligence efficiently. But here's the critical boundary. ISIS gives the fabric underlay reachability between fabric nodes and tunnel endpoints. It does not provide endpoint ownership or mobility truth. It also does not carry endpoint mobility state in the ACI sense. If a workload moves from one leaf to another, that location truth is not an ISIS job. And it does not express the higher level policy semantics that people often associate with ACI as a whole. ISIS is transport logic, not the full ACI brain. A simple way to say it is this: ISIS answers how the fabric gets to the destination fabric node over the underlay. It does not answer where is that virtual machine right now or what endpoint behind that tunnel should receive the packet. That separation is healthy. It lets the underlay stay stable and efficient while endpoint intelligence can evolve independently above it. So whenever you hear that ACI uses ISIS, think built-in underlay reachability, loopbacks and taps, fast convergence and ECMP across the fabric. Think roads and routing between switches, not endpoint ownership. Once that clicks, COOP makes sense as the missing answer to a completely different question. Now for COOP, which answers the question ISKeys does not answer. Which leaf currently owns this endpoint inside the fabric? In practice, think of COOP as ACI's internal endpoint location and ownership mechanism within the fabric control plane. Endpoints are learned at the leaves because leaves are where servers, VMs, and other attached devices actually connect to the fabric. When a leaf learns an endpoint, it reports that information upward so the fabric can maintain an authoritative view of which leaf currently owns that endpoint. That authoritative database role lives at the spine layer in the COOP system. The spines are not just transit here, they are part of the endpoint directory function. This is why COOP is so important. If a source leaf wants to reach a destination endpoint, it needs to know which destination leaf currently has that endpoint attached. Without that answer, the fabric would know how to traverse the roads, but not which driveway to pull into. Leaves do not have to store every endpoint in the entire fabric all the time. They can cache selectively based on what they need to forward traffic efficiently. That selective caching helps scale. The fabric can maintain central authority for location while avoiding unnecessary full distribution behavior everywhere. Virtual machine moves, new location becomes authoritative quickly. COOP is what keeps endpoint ownership and location truth current inside the fail once move. That way, traffic gets sent to the right leaf instead of a stale one. That makes COOP central to mobility handling. It is not just a lookup convenience, it prevents forwarding decisions from drifting behind the actual workload location. A good mental shortcut is this: COOP internally answers which leaf owns this endpoint now. Notice what COOP is. It's not the underlay routing function, and it's not the external or remote reachability mechanism. It's the fabric's internal endpoint location function. Its scope is local fabric endpoint location. That scope is exactly why it is so effective inside ACI. If ISIS gives the fabric reachability to the destination leaf deep, COOP gives the fabric the current knowledge of which leaf owns the endpoint. Those are two different control plane answers, and ACI deliberately keeps them separate. That separation is what makes the next layer, MP-BGP EVPN, easier to place in the overall picture. Now let's add the third piece, MP-BGP EVPN. This is where many engineers start to blur roles, so the boundary really matters. MP-BGP EVPN becomes relevant when reachability has to extend beyond the local fabric's internal endpoint location problem. You'll usually see MP-BGP EVPN show up around three situations: L3 out, multi-site communication, and any case where route information needs to move beyond the local fabric. BGP is a natural fit for that job because it is already the protocol engineers trust for exchanging routing information between different systems and administrative edges. EVPN adds endpoint-aware signaling semantics that make the exchange more useful for modern data center and overlay scenarios than plain older route exchange alone. But here is the key. Inside one local ACI fabric, COOP still answers which leaf currently owns a local endpoint. MP-BGP EVPN does not replace that local fabric ownership function. It complements it when the destination is outside the immediate local endpoint directory scope. So think of COOP as a fabric's internal address book, while MP-BGP EVPN is how that fabric exchanges reachability with places beyond its own walls. In a multi-site scenario, that matters a lot. The local fabric still needs local endpoint truth, but the broader system also needs a way to advertise and learn remote reachability. In an L3 out scenario, the idea is similar. You are crossing from the internal fabric world into external routed domains, so BGP-based exchange becomes the sensible tool. This is why saying ACI uses MP-BGP EVPN does not mean EVPN is running the whole local fabric forwarding story by itself. It means EVPN is carrying the right kind of reachability information at the boundaries where inter-domain exchange matters. The local fabric still depends on ISIS for underlay transport and COOP for local endpoint location. A useful way to place EVPN is this. It tells the fabric about destinations beyond the local endpoint directory or about remote reachability that must be imported and exported cleanly. That is why EVPN complements COOP instead of competing with it. They solve different reachability scopes. Once you treat local endpoint ownership and external or remote site reachability as separate jobs, the control plane becomes much less mysterious. Now let's tie all three layers together in an actual packet journey, because that is where the design really clicks. Let's make this real with a packet walk. First case, a source endpoint on one leaf wants to send traffic to a destination endpoint somewhere else inside the same ACI fabric. The source leaf can learn the source locally because that endpoint is attached right there. But for the destination, the source leaf needs location truth. Which leaf currently owns that destination endpoint? That is the COOP moment. COOP provides the answer about the destination leaf associated with that endpoint inside the fabric. Once the source leaf knows the destination leaf, it can encapsulate the packet toward the correct tunnel endpoint. Now the underlay takes over. ISIS has already built reachability between the fabric nodes, so the packet can travel across the spine layer toward that destination tip. Because the fabric is leaf spine and the paths are equal cost, the traffic can use available spine paths efficiently instead of depending on one rigid route. The destination leaf receives the encapsulated traffic, decapsulates it, and forwards it to the attached endpoint. So in the local fabric case, COOP answers where and ISIS answers how to get there across the underlay. Now change the scenario. The destination is not just somewhere else in the local fabric, it is behind an external routed domain or in a remote site. In that situation, the fabric needs more than local endpoint ownership. It needs reachability information for something beyond the local COOP scope. That is where MP-BGP EVPN comes in. It supplies the route and reachability context for destinations outside the local endpoint directory problem. Once the right exit path or remote reachability is known, the packet still uses the local fabric underlay to get to the correct place to leave the fabric or reach the right transport point. So even in the remote case, ISIS is still carrying the packet across the local roads. EVPN is adding the beyond local fabric map information. If you remember one model from this video, make it this. Hardware sets your scale and feature ceiling. ISIS builds underlay reachability. COOP tracks endpoint location inside the fabric. MP-BGP EVPN extends reachability beyond it. Now that the fabric itself makes sense, the next question is how ACI turns applications and connectivity into policy.